Swayam Prabha. Digital India. Educated India.
So in this lecture, we'll discuss about time correlation functions and the relationship to transport coefficients. So these time correlation functions can be calculated in MD simulations, and we can use such functions to obtain transport coefficients such as diffusivity, viscosity, thermal conductivity, and so on. Now, this time correlation function is basically used to relate two time dependent functions. For example, think of two functions A and B, which are time dependent signals, and the time correlation between these signals A and B is related by this equation, which is basically a product of the value of A and B separated by a time interval t, and then this is integrated over different initial time origins. The meaning of this equation can be explained using this particular plot, where signal A and signal B are plotted as a function of time for a small segment of time. Now we choose a particular time t0 at which we pick up the value of A, and then we choose another time t plus t0 at which point we pick up the value of B, and then we make a product of these two numbers A and B. So that is done for one particular choice of t0. Similarly, we take another set of such data points by choosing t0 somewhere else, and then another point t plus t0, and then getting the value of A at a t0 and the value of B at a t plus t0, and then taking product of this, and then you sum over many such choices over sets of data which are all of them separated by a time interval of t, and this will give you the correlation function of C at a given time t. Now if you want to calculate the same quantity for C of 2t, then I should be taking a time point t0 and then another point at t plus 2t plus t0. Okay, so I have to collect sets of points which are separated by a time of 2 times t, and so on. So you are able to then collect many such sets of data separated by the same time delay, and then you average over many such choices of data, and that allows you to calculate correlation time or correlation functions of A and B as a function of time. So this is a function of time itself. So what is the meaning and use of such a time correlation functions? So this is a definition which we shown as a time integral, and equivalently we can also write this as an ensemble average over many initial points tau naught. Okay, so it's an ensemble average of A times B, except that this A and B are not taken at the same time points, but they are taken at a delay time of t. Okay, so thereby the function C is going to be function of time. So the ensemble average basically measures the correlation between the values of A at a t0 and B at t plus t0. So that's the meaning of time correlation function. Suppose if you imagine these functions A and B are not related to each other and these two are independent signals, then when you operate this particular equation, you can show that the time correlation function is simply given as the product of mean of A and B. That is, we calculate what is the mean of A over ensemble average or time average, and then multiply that with the mean of B, and you see that then C of t becomes independent of time, okay, when this signal is uncorrelated. But if A and B are related, then this C of t may differ from these asymptotic values. Now if A and B are two different quantities, then we call this C of t as cross correlation functions. So cross because it's a two different variables, so we are crossing between two different variables and then finding their correlations. Sometimes if A and B are the same variable, then we call them as a autocorrelation function. Okay, so we either use cross correlation if A and B are different, and autocorrelation if both variables are the same thing. So we correlate the same data separated by a particular time interval t. So what is the use of such a time correlation function can be illustrated with this example, where you have some signal A which is smoothly behaved, and then you have another signal B and which looks very noisy. So, if you want to know whether this B of t is related to A, we can actually take a time correlation between AA and AB and then they compare them. So, this is what is compared here. The solid line here is the autocorrelation of function A, that is the continuous line, and then this the cross correlation between A and B is given by the dotted line, and you can see that they are very similar in nature. So, when you look at the signal, absolute signal themselves A and B, they look very different, but then if you correlate between AA and AB, you see that they are basically identical to each other. In fact, in this particular example, this B of t is nothing but A of t with some random signal added, okay, and because of which A and B are correlated. Suppose if this B was not at all related to A, then you will not see a good match between autocorrelation function AA and cross correlation AB, and AB will be something like close to 0 if it had been not related to A. So, this would have been your A dot B or AB for a uncorrelated signal B. But in this case, because B is highly correlated, you can see that both autocorrelation and cross correlation functions are very identical to each other. So, we are able to tell by measuring the autocorrelation function and cross correlation functions, we are able to decide whether two signals are identical or not. So, now we would like to look at what is the limiting behavior of these functions at short times and long times. So, let us say when t is close to 0, tending to 0, that means you are looking at correlation between two sets of data which are in the neighborhood of the same time, okay, they are not very far apart, they are very close to each other in time. So, then we use this definition of correlation function and we substitute t equal to 0. So, here we had c of t, now I am calculating this function at time t equal to 0, and this variable b is also taken at the same time as a, okay. So, that is why here it basically becomes an ensemble average of a at t naught and b at t naught. So, we are actually taking the values of a and b both at the same time point, because we are interested in correlation at a t equal to 0, and then this becomes nothing but the ensemble average of AB, and this is something we call it as a static correlation, because this becomes independent of time because it is locally constant value. And you may also relate that we have been talking about fluctuations in the previous few classes, where the fluctuation in two variable a and b are related by this function, which is the joint correlation of a and b, mean of a b minus the product of mean of a times mean of b, okay. So, you can see that what we have called as a static correlation function in the limit of t tending to 0 is basically related to our fluctuation definitions. We will make this link little later at some point of time. So, this is what you expect at a time t equal to 0, the correlation function to be Whereas, when t gets to a large value, when t is very large, then you see this a and b becomes uncorrelated and they become independent signal. Then you can show that c of t will be simply a product of the means of a and b, okay. And this is true as far as we are talking about non-periodic functions. If it is a periodic function, this will not be uncorrelated at long times, it is only for non-periodic functions. So, thereby we can show that the c of t basically ranges a maximum value of this mean of a b to a product of mean of a and mean of b, okay. So, this is a range at which the c of t, which is time correlation function, is likely to vary. So, now what we can do, now that we know the maximum value of c of t can take, we can actually define a normalized time correlation by dividing c of t by the maximum value, which is mean of a b, okay. So, when I do this normalized time correlation function, which is denoted as small c of t, and you will see that this small c of t ranges from maximum value of 1 and it reaches at a time t tending to infinity or large values, you see that this goes to the product of means of a by a times b divided by the mean of a b. So, this is the value that it approaches at very large times. Now, suppose if one of a or b mean is 0, then you can see that c of t will go from 1 to 0. So that's a range of time correlation function. So pictorially it is shown here, but now I am trying to simplify this to time correlation to a autocorrelation function. That is, I am taking both A and B the same. So the autocorrelation function is written as the ensemble average of value of A at a t naught multiplied by the same variable but taken at a different time t plus t naught. Thereby, two such values of A are separated by a time interval of t. So then the values of this function will range from the mean square to the square of the mean. Okay. So this follows from our initial the previous discussion, where for A B this was like this. So when A and B are the same, it becomes A square. Okay, that's what is being shown here. And similarly, this becomes the product of means of A and B becomes the square of the mean. Okay, so this is a limit for the autocorrelation function of the same variable. And in this case also we can normalize the time correlation function with the maximum value, which is the mean square. Okay, thereby this normalized correlation function will range from 1 to the ratio of mean square by the square of the mean. And if mean is 0 for a particular variable A, then the C of t will range from 1 to 0. It is actually graphically shown here. At a time t equal to 0, you see that this starts at the mean square, and then in the limit of very large time it saturates at about the square of the mean value. Okay, so this is how you will expect the time correlation to behave. So what we are trying to see by this is that at a time t equal to 0, at a very closely spaced time intervals, these variables are highly correlated. Okay, and as you go to larger and larger time delay, this correlation basically decays. Okay, so that's the information that we obtain from such a correlation or autocorrelation functions. So now we are going to just work with this limits and then try to renormalize in such a way that this function will go from 1 to 0. So now to recollect what we have discussed so far, so we have this unnormalized time correlation function, autocorrelation function in this case, which goes from mean square to the square of the mean between very small times and very long times. Then what we said, we can actually normalize this function with the initial value so that it starts at 1 at time t equal to 0. So the relationship between these two equations is simply taking this equation and dividing by the maximum value, which is a mean square. So it goes by 1 and then decays to the square of the square of the mean divided by mean square. Now if you want to shift this function, what we can do is we can subtract from this value the mean square and then divide by the height of this function, which will be the mean square minus the square of the mean. So when you transform this equation, what we are able to show is that this function will now go from 1 to 0. So we will use this as the final definition of time correlation function, because it nicely goes from 1 to 0, where 1 means the variables are highly correlated and when 0 means these are completely uncorrelated. Okay, this is a time at which the signals become uncorrelated. So now what we are going to do is we take the definition of the normalized time correlation function, which goes from 1 to 0 in the limit of t equal to 0 to t equal to infinity. Now what we want to do is we want to relate our definition of fluctuation, which we have seen before, where sigma square of a variable A is written as ensemble average of delta A square, which is nothing but the ensemble average of delta A, but only thing is we considered both of these functions at the same time t when we talked about fluctuations. Okay, and then we can show that this is shown as the mean square minus the square of the mean. So this is something that we have discussed in fluctuation theory. So now we want to relate this fluctuation to time correlation function, and the difference only is that here we correlate the variables at the same times, whereas in the time correlation function we correlate between two different time intervals, two different time points. So let's use those description so that we can show the relationship between the two. So I take this equation and then I write the first term, which is the ensemble average, remains as it is. So this is the square of the mean, which I can write as the mean calculated at t naught and the mean calculated at some other time t plus t naught. Okay, and since the mean is independent of time because it's an equilibrium property, I am allowed to write the a in terms of t naught and t plus t naught. And then if you look at the mean square minus square of the mean, that is our definition for sigma square. So that I am substituting. So then by comparing this with these equations, okay, so we can show that this entire numerator can be simply written as delta A evaluated at t naught and delta A evaluated at t plus t naught divided by sigma A square. And this is nothing but our correlation function evaluated at time t, and this becomes nothing but time correlation function evaluated at t equal to 0. So the normalized time correlation function basically is a unnormalized correlation function divided by the same correlation function of t equal to 0, because that is where this function goes to maximum value. Now this is done for autocorrelation function, and you can do the same thing for cross correlation function between CAB also, where we replace one of them into B. So we write ensemble average of delta A delta B, and you can see A is measured at t naught and B is measured at t plus d naught, and then divided by the respective standard deviation of A and B. Okay. In other words, similar to this, you can also show that the normalized autocorrelation function between A and B can be related to the unnormalized time correlation function at time t divided by the same value at t equal to 0. So now let us look at how the time correlation function behaves for certain variables. So here on the left hand side, we are plotting the velocity autocorrelation function for a liquid. Okay, so you have a Leonard-Jones liquid, and then we have this velocity for each particle, and then we autocorrelate the velocity of the variables, and you can see that as we expected, it starts at 1 and then it tends to 0 at long time intervals, and then depending upon the density and temperature, you see different kind of behavior. If you consider this, which is a density of 0.6 and temperature of 0.95, you see a monotonic decay from 1 to 0. Whereas if you look at this curve, which is corresponding to a density of 0.85 and a temperature of 0.86, you see that up to certain point the velocity autocorrelation function is positive and then become negative, and then eventually it also catches up to 0. So what is the meaning of positive values and negative values? So positive values means that these velocity directions are in the same direction, whereas when these values are negative, it means the particles are pointed in opposite directions. The velocities are opposite to each other. So negative correlation means they are in the opposite direction, whereas when they are positive, that means they are in the same direction. So the autocorrelation function basically tells you what is an average relationship between the variable and that how that decays with the time. As far as the time is concerned, long time behavior is uncorrelation, whereas at a very short time there is a high correlation, and in between you see a complex behavior depending upon the thermodynamic state of the system. So here you can also write a similar kind of a time correlation function for a orientation of a molecule. Okay, so if you have a non-linear molecule, and then if you define a particular orientation u, and then you ask what is the correlation between such linear molecules. So if the correlation, if the molecules are highly correlated, you will see that it will be positive value, and when the molecules are arranged opposite to each other at a certain level, you will see negative correlations, and you can see that this value, it starts with 1 by 3 because the C of t itself is defined with respect to 1 by 3, whereas this value itself will be only 1 at time starting at time, and then it has a positive correlation and then goes to negative values. That means the directions are opposite, the orientations are opposite, and then again there is a certain time at which it becomes correlated again, and then becomes a oscillatory behavior, eventually leading to 0 value at a long time. So in about a picosecond time scale, that is 10 power minus 12 seconds, the correlations kind of vanishes. So that means if you look at molecules at a microscopic level, there seems to be a orientational correlation. So depending upon the one molecule's orientation, the other molecule's orientation is affected, and they are related for a time period of about 1 picosecond. Beyond that, these molecules do not relate or influence each other. So that's the meaning of the time correlation function and its decay. And then if you look at a liquid, you can see that the correlation function just monotonically decreases from some initial value. So you can also, like a GFR, where we had a structural information, by looking at the patterns of GFR, we can use this time correlation functions to relate what is the correlation between different variables in the molecular system. So now all these introduction that we talked about for time correlation function is because we wanted to relate this to certain transport coefficients. And this is possible because if you look at the theory of transport coefficients, they can be actually mathematically related to the how the system responds to a small perturbation, and the response of the system to a perturbation is captured in the time correlation functions. Then there should be a relationship between the transport coefficient and the time correlation functions. For example, if you are interested in diffusion coefficient, this is nothing but a response of particle flux to an imposed concentration gradient. So when you impose a concentration gradient, that's a perturbation, and you see the response, which will be a particle flux moving in a particular direction. And this magnitude of this flux is governed by a diffusion coefficient. Similarly, if you look at shear viscosity, you take a fluid and you apply a velocity gradient, that's a perturbation, and then the fluid will exert a shear stress, that's a response. Thereby, the shear viscosity will relate the applied velocity gradient to the developed shear stress. Okay. So now we have an empirical or phenomenological transport coefficients relating response to a perturbation, and then equivalently we have developed this time correlation functions that captures how far these perturbations are causing response to a system. Thereby they can be related to each other. Now, without going to the theory of showing the equivalence of these arguments, we will take these results as a as given. We are interested in two sets of relationships. One is called this Green-Kubo relations that relates the transport coefficients to a time correlation functions, and then there is another set of relations called Einstein relations, which again relates the transport coefficients to the mean square values of the certain functions. Okay. So and now we can replace this, we can write a set of Green-Kubo relations and Einstein relations for diffusion coefficient, shear viscosity, thermal conductivity, etc. For example, if you are interested in this diffusion coefficient, the diffusion coefficient is related as 1/3 times the time integral of the velocity autocorrelation function. Okay. So here I means for a given ith particle. So in principle, diffusivity can be obtained by looking at velocity autocorrelation function of a one single particle in the entire system. However, good accuracy, we can basically average over all the particles in the system. That means we take autocorrelation function of all the particles and average over the number of particles. Thereby we get a much more smoother autocorrelation functions for velocity. Okay, this is something we have already seen, how the autocorrelation function varies, and the time integral of this curve is what is related to the diffusivity. So in simulation, we are actually hoping to calculate the time correlation functions of velocity or velocity autocorrelation functions, and then do a time integral numerically, and that will give you diffusivity. So that's a way to calculate diffusivity in one particular method. The other method is using this well known Einstein's relations, which relates the mean square displacement of ith particle to the diffusivity. This also can be averaged over n number of particles for good accuracy in statistics. Now, when we do this mean square displacement calculation, we have to be careful because these are the absolute positions of the atom at a given time t, whereas in our MD simulations, we often apply periodic boundary conditions. That is, when a particle moves out of the simulation box, we put it back from the other side of the simulation so that we conserve the number of particles in the system. Whereas such a data will not be useful for calculating diffusion coefficient or the mean square displacements. So what we need to do is we have to bookkeep the actual particle positions as a function of time, and we have to apply periodic boundary condition only when we want to calculate minimum image convention and force calculations. Okay, so that's a extra care has to be considered. The second important transport coefficient is shear viscosity, and the shear viscosity is given as volume divided by kVt time integral of the stress autocorrelation functions. So, the stress autocorrelation function is related to the pressure tensor, and the alpha beta is basically refers to different components of your stress, and the stress can be calculated by two components, one that coming from momentum contribution and the other one coming from force contribution. So, here unlike the velocity autocorrelation function, which is a single particle property and then it can be averaged over many particle, but here in this case the stress or the pressure tensor is a collective property because it is summed over many a pair of particles. Okay. So, in this case there is no possibility of averaging over n. So, because of this, usually when we measure in simulations, the viscosity calculations would be a little bit more noisier than the calculation of diffusivity, because diffusivity allows us to average over n number of particles, whereas in the case of viscosity it is related to the pair averaging of the virial and the momentum, and such improvement in accuracy is not possible. And we can also write the thermal conductivity by analogous Green-Kubo relation, which is V by Kb T squared, and then time integrating the energy current of the particles. Okay. And so this J alpha here is basically the component of the energy current. So, this also is something one can calculate in MD simulations, and then once you get the energy current autocorrelation function, that can be time integrated to get thermal conductivity. So, in summary, we looked at a definition of cross correlation and autocorrelation functions, the definition, mathematical definitions, and the limiting behavior at time t equal to 0 and time t equal to infinity, what is their behavior. And these time correlation functions are related to transport coefficients such as diffusivity, viscosity, and thermal conductivity. And this TCF may be a single particle property like velocities, or it can be energy, or it can be related to sum over pairs of sum over many pairs like virial, etc. And we also show that these relationship between the time correlation function to transport coefficient is given by this Green-Kubo relationships, or analogously Einstein relations, comparing the transport coefficients to mean square values of the time varying quantities.